Alright, so looks like the stream crashed last time, but we finished some things and we're gonna pick up again today after we check the archive for a little bit. So, let's do a little quick check, see if alright, we're gonna just remove that. Probably gonna remove this too. Oh, nope, we're back. This one turns it off though. Okay. All right. Hopefully that's good enough, as it is. I like the principle of this this archive post, just the compgit package, computational tool for geometric invariant theory, quotient. Wonder if that is supposed to be quotient or actually just quotient. Geometric invariant theory quotients. Okay, just ends a little bit early. But I just feel like in general lately I've been excited to see more computational things show up on the archive. So Quiver Tools package for Sage Math and Julia. It's like basically very similar to the previous thing. That's actually kind of rare. Peter Bellman's is doing a lot of computational stuff though. So it's cool seeing more of this come out. We introduced Quiver Tools, a new software package available in both Sage Math and Julia version to study quivers and their moduli spaces of representations. kind of thinking, fuck this music, honestly. But, maybe it's fine. No, I'm not gonna listen to it. Alright, let's try something else. I feel like slow is just not where I want to be right now, which makes it difficult. I also kind of don't want to listen to that again. Fuck. 99% of this is going to be just me picking out music. Okay. Nothing that I'm immediately trying to look at. We're running this in the background. Had to restart because my power went out last night. And what we want to do right now is twofold. So what we're trying to find out is if some similar computations will work for kind of other Herzberg surfaces. So one of these should be potentially given by this ideal inside this ring. So that should be the Segre embedding of another Herzberg surface, F4. But I'm not convinced that it is, or I'm not convinced that some functionality in Macaulay 2 is working the way that I think it is. So for example, let me just take this and let me check. So what we're going to do is we're going to have K, it's going to be the canonical divisor for S, and make sure that it's graded. Okay. I think this is weird. Mainly because, so here C, this is supposed to be the curve section of this projective bundle, which has unique self-intersection, which is -2. And the canonical divisor, and then F is supposed to be a fiber under one of the projections. So, sorry, under the projection giving this variety the structure of a projective bundle. And so the canonical divisor should be -2 times C plus -4 times F. And we're getting -2 times C coming in here. And then there's two other components which are kind of weird. So if I have x3, x2, x1, x0, then what is going on with that? So I wrote this down yesterday just to check what that implies. So if x3 is 0, x2 is 0, x1 is 0. Oh, sorry, no. If x0, x1, and x2 are all 0, that says that the first coordinate is 0. Okay, so the second coordinate. So this is all embedded inside P1 times P2. And P1, we can imagine having just two homogeneous coordinates, x0, x1. Maybe I say W. No, I'm going to say like little x0, little x1. And then P2 is going to have homogeneous coordinates, little y0, little y1, little y2. And then these x's are the products. So x0 here is little x0 times little y0. And x1 is little x0 times little y1. And so in this case, actually, the divisor x3, x2, x1, x0, it should be linearly equivalent to the divisor x5, x4, x3, x1. And so if we say, so is linear equivalent -2 C -4 F and K, then the answer should be true. Okay, that's great. What I think is weird is, okay, so let's quit this and restart it. And so now I'm going to load in effectively what should be something very similar. Okay, actually, what is K? So here we have -2, -3, and a plus something. Okay, so in this case, let's see. I think that, okay, one of these, at least F, I think, should be the same fiber. So now we're working with F4, Herzberg surface, which is projectile relation of O plus O4. And so the fiber of that P1 bundle, I think, is still given by this vanishing X1, X3, X4, X5. The one thing that I'm not totally convinced by is that the section is given by the vanishing. So the unique section with multiplicity, or self-intersection -4 in this case, is given by this vanishing of this ideal. But I kind of think that it is. So then what should the canonical divisor be? It should be -2 times this section C minus 6 times this section F. So and that is false, right? So that's weird, right? And kind of what that tells me is that okay, what that tells me is that my equations are not totally correct. They are producing a surface, and it's a smooth surface at that, so that's not awful, but we might have to just actually write down what the equations are, but I want to check with what was listed. So how many days? Okay. So let's see. We've got x0, x4, x1, x3, x0, x5, x2, x3, x1, x5, x2, x4, x0 cubed, x1, x3 to the 4th, x0 squared, x1 squared, x3 cubed, x4, x0 squared, x1, x2, minus x3 cubed, x5, x0 times x1 cubed, minus x3 squared, x4 squared. And then we got x0, x1 squared, x2, minus x3 squared, x4, x5, x0, x1, x2 squared, minus x3 squared, x5 squared, x1 to the 4th, minus x3, x4 cubed, x1 cubed, x2, minus x3, x4 squared, x5, x1 squared, x2 squared, minus x3, x4, x5 squared, x1, x2 cubed, minus x3 times x5 cubed. Those look, okay, those look actually correct. So that's no good. So one thing that I can do is just check if the thing that I okay, so one thing that I'm not convinced by is so I guess maybe just that the canonical divisor function is not doing what I think it should. So let's try just doing this directly. Okay. Yeah, that's probably not good either. So let's do okay, so this should just be already what we want. So if I calculate this is actually the right thing. Okay, yeah, so somehow the canonical divisor, I mean, so this is giving me the right thing. So somehow the canonical divisor function is not doing what I think it should be doing in this case, I feel like. So I can pull up the source for the canonical divisor, right? So we input a ring, we can say that it's graded, and it's going to compute the canonical divisor of the ring. Warning, the canonical divisor is not unique, but only unique up to linear equivalence. Somehow we're getting something that doesn't even seem to be true. If the is graded option is set to true, then it's going to return a canonical divisor for the proj of this ring. Right, and we're making sure to specify that. The graded version only works reliably for graded rings over a field, which we are in the situation of. So, it is weird that this is doing something that I wasn't expecting. So 10 is actually the answer that we did expect. So it looks like we could try messing around with this one. So let's try what do we want? So we want to do 4 times m. So let's set up m4 to be OO of we're gonna do 4 times everything. So 8 times C plus 24 times F. But I'm going to add 1. So just make it directly like this. We're going to say, let's take this guy and make it bigger. Okay, so actually a couple of things. Okay, so there's a few things that I want to run by. One is so I want to verify that a couple things. So what was this module that I just defined? M4. So one, the big thing that we want to check is P4 times M4. So we'll call this, we're going to call it N. 4. P4 times M4. This should produce for us a module, which, if we're lucky, has depth 2, but probably has depth 1. If the module has depth 2, then we can use the Hilbert series function to essentially calculate the global sections of the sheafification of this module. And otherwise, we need to saturate it first. So I want to check, well, what should happen when I take this M module, which is representing the canonical, the anti-canonical. It's a module which represents the anti-canonical divisor. I'm going to tensor it with, or multiply it against the ideal of these 9 points, and calculating the global sections of that thing should produce the linear system, or the anti-canonical divisor on the blow up of F4 at 9 points. So since it has the anti-canonical divisor in this case has dimension 10, the blow up at 9 effectively general points should give us a linear system of dimension 1. So that's before quotienting by the scaling action. So effectively 1 effective divisor in this linear system. This is kind of a mess. I'm not keeping workspace very coherent or organized, but that's somewhat okay, I think. I could probably just cancel this computation, because I think it's going to end up coming out as being 1. But let's delete this, since I don't think it actually is going to be accurate. Right, so the canonical divisor in this case is -2. Let's do anti-k. This is... Honestly, I think also it's probably not beneficial to have modules that we're going to end up tensoring a whole bunch. So I can either define this, I'll just define it. It's not going to hurt. But doing anything in particular is probably going to be more efficient to just define a whole new module from the get-go. That's what my experience has told me, at least. I'm kind of curious why the canonical divisor wasn't giving me what I wanted. So we can go to Carl Schwede's paper, which explains it maybe. So it's potentially just my own mistake. It's worth mentioning that the function canonical divisor simply computes the canonical module via an appropriate x and then calls divisor on that module. If you wish to construct a canonical divisor on a projective variety, make sure is graded option is set to true. So I wonder if calling the canonical divisor in this way requires something about like a embedding of locally complete intersections, maybe it requires like a complete intersection variety, which the thing that I'm giving it is not. Or is it sufficient to just do so let's pull up this guy and just close it out and pull up this guy, close that out, and then swap these two if I can. I'm like traumatized from fucking around too much with this tiling manager from yesterday. So what do we need to do? We need to go to Hartshorn. effectively always my source for trying to sort these things out. So maybe I should know this off the top of my head, but constructing the canonical divisor via some X groups. So we embed X as a closed subscheme in some projective space. We take the canonical to be some X sheaf of our structure sheaf going into the canonical for this projective space. And what we get is the canonical divisor on X, right? And the only thing that we need for this is that our scheme is Cohen-Macaulay and we have something smooth. So I wonder if, yeah, how could this be getting messed up? I'm not exactly sure how it could be getting messed up. I guess there could be some weird calls. Maybe some things should be saturated before they go into... So like, I wonder if this ideal I is saturated, for example. True. Maybe you need, in order for this computation to work in Macaulay, the embedding to be projectively normal, which would be weird, but also, is this embedding not projectively normal? I'm not sure. Guess we could check that though, right? So Hilbert series on I. So let's do II is modulo of I. And let's do Hilbert series of II to order, who knows, like 6. Okay. So already in degree 2, it's not giving us 0. So what that should mean is if we twist this ideal sheaf by that's giving us global sections, isn't it? What we really want is HH of 1 of I, II, and then don't know if this is gonna work. Yeah. So we could just try like doing this, and then doing like that. Could make it a sheaf. So F, let's do Y is sheaf of II. And try computing this. Okay. So that kind of confirms at least. Right? It's not linearly normal. It's not quadratically normal. But it is cubic. Quartic, quintic, probably everything higher than that. I wonder if this has to do with the fact that the ideal that we produced has generators that are kind of all quartic of degree. Okay, so I think that could be a problem. And I might check it out later. But let's try taking N4, which has depth 1, and we need to saturate it. So sat N4 is going to be saturated. I think that's probably going to take a little bit. And right, so what we need to do is check. So we'll do capital anti. Okay, it's going to be P times anti-K. And we want to check Hilbert series of anti-K to order just 1, just to verify the global sections. And then also to calculate minus G, so vanishing sections for minus G. This one should be, let's call M to be OO of, what was the module that I picked? So I think it's 8 times C plus 25 times F. And P4, it's going to be intersect all these guys, but to order 4. Then the next thing to do is just multiply them. So say N is P4 times M. Saturate. And then call Hilbert series. And this one, since we've done it in this way, we can just call up to order 0. Sorry, 1. Okay. So that should be effectively doing what we're doing, and this should this should somehow be the reproducibility for this call. Alright, so what to do in the meantime, huh? Just casually browse math jobs, maybe? There's actually like the first couple positions being posted for the year again. We've got a tenured tenure track faculty position at St. Olaf College for $74,000, $79,000 salary. Teaching 5 courses per year. All right. So, maybe we just look for the source code for this function. I can't remember where it's located. Kind of don't think this is it. Not only because I can't find the divisors package, but I think this is just going to be that actually kind of is it. think it actually is maybe in here. So it just constructs it as an X. Of the appropriate codimension. S1 to the 1 mod I1. I'm not sure how it would call. I'm not sure how this flag is operating. So if the method is set to false by default, then it does this. And then don't know what this means. So S1 is the ambient. And this one you'd think would give us the regular one. So this is like if we took our projective variety and its structure sheaf. And then you have to send it into the ring. Twisted by minus some of the degree lists, huh? So I don't know what raising this ring to this power is supposed to do, for one. Summing the elements inside the degree list. So it's taking just those elements generating the ideal and summing their degrees, which is hard to believe that that's what is going to end up computing this canonical divisor, I guess. Okay, so maybe we can do I think there's a lot more subtlety using this canonical divisor. Alright, check on the other one. That one's still ongoing. This one's still ongoing. I think that we could have made this go faster by just computing a much lower or a much smaller module. So we didn't have to compute the saturation of N4. I made this a huge thing, and it's probably, this might take, I mean, potentially this could take, like the main step that's being locked down in this program is probably also a saturation of some module. And so it could be faster for me to cancel this and try to actually compute which twist I would need to operate on to saturate this guy. But I might just take a little break for lunch and then come back to it. Or at least I'll go grab some lunch and then I'll come back. Okay, we're back and finished with this. So I realized the issue was essentially the projective normality. Calling, maybe I did it before this, whether or not this ring R mod I was normal, and it wasn't, which we could have seen just from that one computation of the cohomology of the ideal sheaf. So, right, so we had to use instead these modules constructed explicitly from C and F, and I think this should be fine. I mean, there's a chance that it's not. So let's do a little quick look, see whether it is or not. Kind of the big function call that we made that I could imagine having a potential problem is the OO call, transferring from a divisor to a module. Okay, so we should take a look at the source code just to make sure that this is something that's not going to use the normality in any crucial way. Who knows? Okay. I think okay, so I think that this is still a correct result. There's a chance that in order to actually have some certainty, we'd have to embed this Herzberg surface into a higher dimensional projective space. I'm effectively taking some very ample embedding, which could be really big. So what is the goal going to be then? So let's try, I think a very ample divisor. So I'll use I know that we're just talking about that this doesn't necessarily work, but let's try C plus 5 times F. Saturate this. Call that. So we'd be working in a projective space maybe of dimension 7. I mean, this is actually something that we could compute without having to rely on Macaulay too. It might even just be available in Hartshorn's book. So we're looking for very ample divisor, effectively, on this ruled surface. Trying to check what the dimension of the linear system is, so. So does this agree with what we just computed? So 2 times n, in this case, is 10, plus 2, that's 12, minus e, which is 4, so that's 8, which is what we got. So we could embed this as a degree 6 curve in P7. Is that what we're trying to do? I think one thing that I'm hesitant about is trying to find the equations for such an embedding. So, I mean, in order to find the equations, if I was actually going to take this curve and try to embed it into P7, which I don't think we need to, essentially, because of like these computations just work. I'm pretty sure also, because in the case where E is 2, we actually get an embedding into 6 minus 2, so degree 4 embedding into P5. That actually is the Cortex scroll that we're working with in the Herzberg surface case, F2. But for F4, okay, how would we get the equations describing this septic scroll? What was it? Sextic scroll? I kind of remember there's something being funny about this too. Maybe the way that this, in the way that we presented the projective bundle, something with this push forward being a little bit weird. Um, Okay, so I think the way that this works is that if we were to do this, what does this say? It says that the global sections of the line bundle that we're looking at, they are effectively given to us in homogeneous forms in two variables of degree n and homogeneous forms in variables of degree n minus e. And so if we took the complete linear system on those things, we just write out, I think, and we can just write out a list of variables like x0, x1, x2, x3, x4, x5, x6, x7, x8, because we're going to be in P7. And then the individual variables, or at least the image of this embedding, will have just these homogeneous forms in the components. And so to get the ideal, we just need to find all the relations between those homogeneous forms. So probably there would be a lot of them. For example, we have something like, right, we'll have like x0 to the 5. And then we'll have x0 to the 4, x1, x0 to the 3, x2, x1, x2. Sorry, x1 squared. I wonder if I can get something that I haven't tried to do yet is get Remarkable onto the computer, and it would be nice to be able to write on the tablet and get it into the screen. So let's see if Remarkable has a app, which doesn't look like. At least it's not provided in the pop shop. Okay, so there's a GitHub for doing this, but yeah. Okay. Well, anyways, all right. So if we were trying to do this using normal embedding, let's try if phantoms are not normal. Then what we'd have to do is effectively, we need to find equations. So we would set up the same business. But now instead of having F5, we'd have X6, X7, X8, looking inside of P7. And then we need to find equations, so for things that look like this. So it would be X0 to the 4th, X1, X0 to the 3x1 squared, X0 squared, X1 cubed, X0, X1 to the 4th, X1 to the 5th, and then homogeneous equations of degree 1. So X0, X1, that doesn't sound right. How many of these are there? 1, 2, 3, 4, 5, 6, 7. Oh wait, 1, 2, 3, 4, wait. 1, 2, 3, 4, 5, 6, 7, 8. Actually, that's right. No, that's not right. There should be one more, right? So let's see. It says inside of, okay, so 2 times 5, that's 10, minus 4, that's 6, so it's degree 6 inside of P7. So we need just that many variables, huh? And then we're good, actually. It should be 8 components, and it's degree 6. Okay, so yeah, this is what it looks like. And it's got homogeneous coordinates. Yeah, a little dangerous, I guess, because this is an embedding which is not so this embedding is going to be slightly different, right? If we end up actually writing out the equations for this thing, then it's going to be normal. It's going to be an embedding, but it's not clearly written as a projected bundle. It's like almost okay. Actually, I don't know. So what's the problem here? I've got a projected bundle over, I've got a P1 bundle, which is the projectivization of O plus O4. And this is sitting over P1. And what I have to do is I have to take the linear system on this P1 bundle, so we're going to call this F4, and it's the global sections of F4 with coefficients in O of C plus 5F. So I agree that we could compute the dimension of this space of global sections using exactly this. The one problem that I'm thinking is, so if I have F4 embedded in P1 times P2, which is another thing, then I want to know what happens to a point in that embedding. So a point of this embedding is going to go somewhere. And so I need to be able to figure out how a point transforms under this, whatever this thing is. So it would be easy if there was like a, well, there might be two. If there was like some canonical embedding into P7. So maybe this is some composition of Segre embeddings and Veronese. Right. So how would I think this is done? So okay, we could try doing like a we could try doing like a degree 2 Veronese from P2 into P, what would it be, 4? So P2 maps to so if I did 2 plus 2, choose 2 minus 1. What is that? 4 choose 2 is what, 6? Is that gonna be P5? So P2 embeds as a Veronese into P5. So I'd have P1 times P5. And then that, under the Segre embedding, goes into 2 times 6 minus 1. It's 11. It's a little bit too big. And so the other chance is if I do a Veronese embedding of P1 to some extent. So how do I have to factor this? So it's going to be a multiple of 3 minus 1. Yeah, I don't think I can get this. Yeah, so I don't think in any way is this... Alright, so I don't think that in any way is this embedding. Alright, that's totally fine. I don't think that in any way is this embedding related to the 1 into P1 times P2. Like, you can't get it through some sequence of... You could maybe get it through some combination of embeddings like this and projections, but okay. Let's try just to... It is annoying, for one, because... Right, so... This feels like it can't be totally true. I think that these should be somehow different. Like, for example, maybe I should have y0 and y1 here. And then maybe we should be looking for... I mean, so they've got to be homogeneous relations, right? Just if we're going to define some projective variety. And if we were just thinking about them in this way, then we would have something like this coordinate squared times this one cubed minus that one is 0. And that's not a homogeneous relation. So this is like y0, y1, where these are both degree 5 for some reason. And then is it good? So what would the kind of thing be here? So maybe not degree 5. I want to say is there some kind of guess that I would have here? So I want homogeneous relations. I want to somehow make sense of this sequence of equalities. And to do that, x0 to the 5th, 0. I think it would be fine to say like this thing to the 5th. Yeah, it doesn't quite work, does it? So there must be there's some subtlety in how you actually do this. This isn't even quite an embedding of P1, right? So All right. I think I might just take a break, go for a little walk, and then maybe come back later. Potentially we pick up from where we left off here. Potentially I make some progress trying to figure out what this linear system should be. Anyways, ciao.